Continuous growth in populations. So again, in the past, when formulas were on your formula sheet for exponents and logarithms, this formula, the PERT formula, was on your formula sheet, so you had to recognize when to use it. Now, if they want to give you a question using this formula, it will be in the question, and they'll explain what each of the parts stand for. But any time that we have population growing continuously, it's going to follow this formula. So just getting used to the formula, here's the situation. Population Vancouver, 1981, 1.38 million. It was growing continuously at a rate of 1.7%. Find the projected population in 2011. So when looking at this formula, we want to now find the amount. We know that the initial amount was 1.38 million. The rate as a decimal is 0.17. And in 2011, that would be 30 years after 1981. This is your most straightforward question because everything's on one side of the equation. You can just type it into your calculator exactly as you see it, push enter, boom, you'd get an answer. Now the answer you get wouldn't come out perfectly, 2.3 million, but this question asks us to round to the nearest tenth of a million. So look at that answer and ask yourself, does that make sense that that's to the nearest tenth of a million? Now anytime we would ask about time with your PERT formula, then you're going to be solving for t. All of a sudden this becomes an exponential equation. When will the population of Vancouver reach 6 million? So this time, I decided not to write all the zeros with 6 million and all the zeros with 1,380,000. Does this make sense? That on the left I wrote 6 million, on the right I wrote 1.38 million. But it's not wrong to write all those zeros. And one of the things that we've been doing throughout is we've been simplifying if we can. So even though the numbers aren't, like that fraction doesn't simplify to something nice, I still divide to get my power all by itself. Just make some of your log laws a little bit easier. So we recognize this equation as an exponential equation because the t, the exponent, the thing that we're solving for is in the exponent. So how do we solve for things in the exponent? We've had two techniques so far. We get the bases the same. Do you have a powers chart for E? No. Would you even know if 6 divided by 1.38 was on that powers chart? No. So we're going to have to use logarithms here. So we take the log of both sides. Now, one of the things that's going to happen when you have formulas that have an E in it, you are going to more often, it's not wrong to take the log of both sides, but you're going to take the natural log of both sides more often. And the reason for that, what's the natural log of E equal to? Natural log of E is equal to 1. Right? Because it's asking E to what exponent is E. The answer would be 1. So because we've taken the natural log of both sides, that allows our exponent to come out in front of the natural log, one of our log laws. And now we can get t by itself. And we just have to divide by the 0.017 because this part is equal to 1. Solving for t gives us 86.5 years. Well, that would be 86.5 years after the time it was 1.38. So add that on to 1981 to get the year. Yes?
Yeah, I think I forget that the natural log of E is like 1, and you put that into your calculator.
It would still give you the exact same answer. So what he's wondering is if he instead also divided by the natural log of E, would it be wrong? No. You type that into your calculator with the natural log of E, gives you the same answer. If you use log on both sides, you have to divide by log of e, because log of e is not equal to 1. Again, a fairly straightforward question. We're getting pretty good at solving for exponents using logs. We've done that a fair bit already. And now we're going to start to look at some of the most involved questions, word problems involving logarithms. So here we got population of a herd of gophers first studied was 15,000. 6 years later, it was 18,000. If the population continues to grow continuously, so that's telling us it's using this formula, again, that would be given to you. You wouldn't have to just know that. How long would it take to triple? So when you read through this whole question, as a student with word problems, you're probably getting pretty good at getting to the last sentence and saying, what do I need to find? And then sort of working your way back and trying to fill everything in. The first question that you have here is, if I want it to triple, should I use the 15,000 or should I use the 18,000? Which one is right? Awesome. Well, when we talked about money doubling, do you remember talking about it taking the same amount of time for $10 to double to 20 that it would take for $10 million to double to 20 million? The same thing's going to happen here. If I set up the equation, if I use 15,000 for the initial amount, then when it triples, it'll be 45,000. I'll still have e to the RT. And if I divide both sides by 15,000 to simplify,